Thank you all for letting me join here the workshop today. My name is Roberto Mostallino. I work as a product marketing manager here in SiPearl. And well, I'm here to present leveraging the API outcome for an open source cloud-based service ecosystem. So the presentation today will be split in 4 different parts. First, we will see the market opportunities into the server, with a particular focus on ARM CPU in the cloud. Then we will see what is the role that SiPearl play in the ARM ecosystem, and also what is the ARM ecosystem in terms of software and hardware. And after that, we will have an overview of the Riser project, what SiPearl contribution is to the Riser project, and what would be after the Riser project. And I will conclude my presentation with SiPearl ARM-based CPU, so presenting our server blade and our first CPU, RIA 1. Let's start with market opportunities. So as you can see here, we have an overview of forecast in terms of semiconductor shipment, divided by multiple segmentation, which are automotive, wire communication, up to industrial and military civil aerospace. And on the right side of the screen, we can see also the major application linked to each of these segments. In total, we say that we have a composed annual growth ratio of 8%, but in the purpose of this presentation, we could focus into the compute part, which represent the server CPU and accelerator card. They could be used for cloud and generative AI. So let's dive a little bit more in detail on this. Here we have data from Gartner analysis, and we have 2 graphs. One is the server revenue by CPU in million of US dollar, and on the left side, on the right side, we have the server volume in kilo units. All these graphs are divided by ISA. So we have x86, we have ARM, we have RISC, other kind of ISA and AI64. What is interesting here to see is that x86 is, of course, the predominant revenue for the server and has a linear growth up to 2028. But not only that, in blue, we have ARM starting from 2022 that wasn't that big, I would say. Yes, I represent probably 10% more or less of x86 revenue. We have that in 2028, the forecast should be that ARM represent or will represent probably 20-25% of the server revenue compared to x86. If we see more in details, what is the forecast for ARM? We have the same kind of graph as before, so server revenue and server volume here. We see that ARM is forecasted to grow with a factor of 3 in terms of shipment and revenue from 2024 up to 2028. So what we see so far is the worldwide market revenue and volume for ARM. But we as a European, we would like also to focus on our domestic market. And the next slide that you can see here represent the revenue and the server volume for ARM in Europe. So the number, of course, are lower compared to the worldwide. Nevertheless, we have a market for ARM that was quite lower in 2022. It was less than $2 billion. It will grow, or is expected to grow up to probably between $6 and $8 billion in 2028. And we can see the same kind of growth for the server volume ARM in Europe. So now that we have seen the revenue of the semiconductor market and particular relation with server and ARM server, I think also it's good to see what is the market share or what we can expect of market share evolution. Here we have 2 graphs. One on the left present the market share by supplier. It's a forecast. It is worldwide forecast. And on the right side, we have the same kind of graph, but is mostly focused on Europe. What we can see here is that in 2022, x86 Intel AMD, they represent almost the totality of the market on the server side. And they will keep the totality of the market probably even for more than 2028. However, the market share, it goes from 90%, it goes down to approximately 80%. On the same time, ARM, which was quite lower in 2022, it will rise up to approximately 20%. So what happened is that ARM is taking the market share partially from Intel, but also from the other ISA. And this kind of market share, of course, with less revenue, we can see it even in Europe. Same trend. So now that we've seen the market, the revenue and the market share for ARM worldwide, also in Europe, for our domestic market, I think it's the right time to go to the second part of my presentation, where we'll see what is the ARM ecosystem, what kind of role SiPearl is playing in it. Let's say that at the present, we have ARM and x86, where ARM is represented by Ampere, which designed CPU by ARM for data center with a particular focus on storage application. And then we also have NVIDIA that design ARM-based CPU, but it's mostly coupled with the proprietary GPU. Not only that, we have different type of hyperscaler, that's AWS with Graviton, or Google with the TPU, or Microsoft that produce their own CPU for their own internal needs, always based with ARM ISA. What we see in the future is that we as a SiPearl, we will have our first CPU, which will differentiate compared to what we have at the moment in terms of ARM and x86. We will differentiate because thanks to the stack of HBM embedded in the CPU, we will be the leader in performance for memory-bound workload. Since the design also is backdoor-free and fully editable, and since we are European, we will play a unique role in our domestic market. And not only that, I will conclude also that thanks to the ARM ISA, we are also cost effectiveness compared to what we have in x86 CPU for the same kind of performance. Let's see now what is this software ecosystem for ARM at the moment. So we have a graph on Gartner here, spider graph, where we see a comparison between ARM and x86 in terms of software and not only software. What we see is that ARM at the moment has a certain advantage in terms of processor core count, price performance ratio, energy efficiency, and also ease of process customization. And well, we can see it since price performance ratio usually whenever you use a CPU like Graviton in AWS, I would say that usually it costs less compared to x86. Since the ARM ISA, how it works, ARM ISA, we also have a certain advantage in terms of energy efficiency, which is becoming more and more important nowadays. And as you can see, since we have a lot of higher hyperscaler type 1 that are developing their own CPU, it has a certain ease of process customization compared to x86. However, as we can see here, the ARM ecosystem in terms of software, even though it grows year after year, is still a little bit behind compared to x86. And we can see a little bit more in details the data center software ecosystem here. So let's consider x86 the most mature one, which is the light blue here. The maturity of ARM versus x86 for 4 different sections here, we can see it is still a little bit lower. For example, the type 1 hypervisor is good because, well, for ARM it works Microsoft Hyper-V, the Xen project, VMware, and KVM. However, in terms of maturity, still a little bit behind x86. And we can say the same thing for the operating system, even though we have Microsoft, a lot of Linux distribution and Apple Mac for ARM. We have containers with Dockers and Kubernetes, and also we have enterprise apps such as Active Directory, Apache, and Java that works with ARM, but we are still merging to grow in terms of maturity. So here is the software ecosystem maturity, but it also is good to see what is the landscape in terms of server base. And what we see at the moment is that we have different ODM and OEM, CPU and GPU provider, and wafer foundries here. So in terms of ODM and OEM, we have Evident, which represent the only European provider for a server, which is here. And then we have HP, Dell, Supermicro, Lenovo. Most of them are American, and one is Chinese. And even though Evident is well known in the HPC field, unfortunately, most of the market in terms of server, general server data center, is taken by HPE and Dell. In terms of CPU and GPU provider, well, we have the well-known AMD, Intel, NVIDIA, Longson, which are American and Chinese. In terms of wafer foundries capable to produce certain process node around 2 nanometers or 3 nanometers, while we have Intel, Samsung, and TSMC, which are American, South Korean, Taiwanese. And well, once we see the landscape, the idea is to see where SiPearl is situated and what is the value chain that can bring SiPearl here. Well, we do not intervene in the first, on the lower part here, which is the wafer fab, because typically it's part of TSMC or Alpha Wave of Intel. However, we, as a SiPearl, we intervene on the full design of the CPU, on the architecture, and also on the software development. From the firmware BIOS up to the server platform enablement. And also we collaborate with partners such as HPE or Evident or Lenovo in order to provide help or a driver for OS or the hypervisor. So now that we know the market and the server software ecosystem for ARM, is the right time to have an overview of SiPearl contribution into the Riser project. So, as Manoli said before, the scope I will just summarize here, but a little bit with less information. The scope of Riser was to leverage the upstream of API and UPilot in order to develop the first all-European RISC-V cloud server infrastructure. And it was done in order to increase our European strategic autonomy in terms of semiconductor technology. We, as a SiPearl in this scenario, well, our contribution was to provide a Seine platform based on real processor with a PCI Express accelerator board integrated with RISC-V, and also to provide a requirement and a use case definition for the Riser prototype. What we still need to do into the Riser project is to provide the Seine platform and to demonstrate the usage of Seine platform for cloud and AI application, bring up the demonstration of the Riser platform, and we're still working on the development of drivers for Riser acceleration and the evaluation of the different use cases. Yeah, I would like to show what we are doing so far in Riser. So we have the hyperstack hardware modules here. And the first part are the DC data center security control module, the host processor module. And then we have the data center XPI module and the smart NIC. We, as a SiPearl, we intervene the first two parts. The first part, we are not the leader. We work with a partner in order to provide a data center security and control module. On the second part, the HPM, the host processor module, we are more into a leader part where we'll provide the HPM using our CPU or an our CPU, combined with a GPU or TPU or XPU. So here is what we have so far for Riser, but After Riser, we have another project called Hire. What is the goal of Hire? Well, we can see it here that in today's model, we have CPU provider, CPU producer that provides CPU, and then the CPU is integrated into a motherboard. And as we can see here, there are different motherboards that integrate different CPU and could be used also in different markets. Could be enterprise, edge, hyperscaler, but at the moment is not standardized. So the idea of IRE and the OCP, Open Compute Project, is to have the new model, what we have here, with the so-called MHS modular hardware system, where each CPU provider will implement the CPU into an HPM host processor module that is standardized in order then to use every HPM in different enterprise, in different market, could be enterprise, edge, hyperscale. So we, as a SiPearl, in Hire, we are our idea is to provide the DC MHS server composed of two parts, the security and control module and the HPM that could be either with RIA2 or HPM with UPilot. We see an example here where we implemented RIA2, and we have also an accelerator card with Riser within the Riser project. So in this context, SiPearl will develop a RIA2-based HPM and X-Axis, and SiPearl will develop also the security control module. For me, this is the end of the third part, and now we are ready to see what is the ARM-based CPU developed by SiPearl, and I will conclude my presentation with the server plate and Seine platform. So our first generation of CPU will be called RIA1 and could be used for HPC and AI processor. Inside, we will have 80 ARM Neoverse 1 core with 2 by 256 SVE each. The particularity of this CPU is the fact that we will have 4 stock of HBM inside and, of course, also 4 DDR5 interfaces. More in detail, our first generation processor is interesting for different reasons. First of all, the high performance per watt. Since we are using ARM ISA, it will provide us an advantage in terms of power efficiency. And thanks also to the HBM, we will have an advantage in terms of high memory bandwidth, which will bring advantage in terms of HPCG or height by per flop. Not only that, we are fully auditable and backdoor free, and we already demonstrate a pre-integration with proven accelerators, such could be AMD, Intel, or NVIDIA. In terms of performance, what we have for RIA1 at the moment is that we will have high value for data access, which means memory bandwidth and stream. Compute power that I measured here in TOPS, since we will talk soon after of AI, bigger than 50. And in terms of energy efficiency, we will have high value of HPCG efficiency and byte per flop. And this could be an interesting value and asset for us, since nowadays we see that in the data center, more and more people are trying to focus on the power, on the electrical power that used to start or to like turn a data center. So here I spoke about TOPS, and TOPS is link AI. And AI, of course, it means LLM. But what does it mean exactly, LLM? Of course, it means large language model. And well, it could be used in a variety of applications. Could be, as we see here, healthcare, scientific research, natural languages, language processing, finance law, security. And in order to build an LLM, we should generally ingest a large amount of preprocessed data to a model in order to train. Then once we have this kind of model, we can use the LLM in different applications. One, it could be to assist or to mentor student or customer or researcher in various expertise domain. One, it could be also to speeding the code development by improving the developer efficiency. And also it could be, in a sense, a companion in order to accelerate the time to market for different applications. So here we have a few considerations for the LLM. First of all is the GPU and cost viability. What it means? It means that company and scientists, they may not be able to acquire or afford, I would say, thousands of GPU simply to achieve what they need to run their own model, simply because the cost is too much, to be honest. And because of that, they may choose an alternative in the market. Then we have what we call the underusage of resources. What it means that using a CPU just to only to orchestrate or to schedule the communication with the GPU, to be honest, is a waste of euro per request. It could be that the CPU could be used for more than that. And well, since the CPU could have a memory capacity, a large memory capacity, we can also use them to handle any sizable large language model. We will see soon after that. In terms of power efficiency, also, I would say that the CPU usually is more flexible in operation compared to the GPU and the market requirement, which is also interesting. Well, I would say that sometimes we don't need something that faster than what people can read, which means that a CPU could be more enough or good enough to certain application. And here we have also politics and sovereignty, which means that depends on who developed the LLM, where the data are stored. We can say that it may have some risk in terms of sovereignty. Because of that, we as a European, we need to develop our own LLM or platform and infrastructure in order to run everything here in Europe. What we see here is the maturity of software for stack of AI or ARMs. I would say that thanks to the proliferation of ARM in hyperscaler, which what we've seen so far was AWS, Microsoft, and Google, we also had a certain boost in terms of maturity for the software stack that could be used for AI. And typically here is an example that what we have so far for ARM in terms of model, framework, runtime compiler, libraries, and hardware. So RIA 1, if we come back to RIA 1, it is developed for HPC and AI application. But why I say that? Simply because some requirements are common to both domain. In a sense, I would say also that AI and HPC, they have similar challenge. Why is that? Because AI tend to be more demanding in terms of memory latency, and HPC tend to be more demanding in terms of bandwidth. So if we have the two domains here, HPC domain and AI domain, we have the requirements that are only for HPC or AI, which are here, but also we have common requirement. One is the power efficiency, because data center cannot increase too much the required amount of electrical power that could be used now and also in the future. And core performance that here is measured in flop, but we also could measure in TOPS. Because of that, we have also tested and simulated what RIA 1 could be, how RIA 1 could be used in terms of AI application. And here we have an example of what we consider to be good for RIA 1. Knowing that RIA 1 support int8, bfloat 16, and other format, we know that that are used into the LLM world. We see here graph where we have the number of parameters here, 1 billion, 100 billion, and 1 trillion of parameters, and what we call the different domain, which is the small language model, large language model, and giant large language model. And based on what we have seen so far, the SLM realm, it's mostly would be mostly addressed using DDR, CPU with DDR in terms of inference. However, the moment that we increase the parameters, we go into the LLM realms. Well, we see a sweet spot for the HBM. But in other words, we using RIA 1, we are able to address both SLM and LLM. However, when the number of parameters increase, it is more wise to use a model that can be exploiting CPU and GPU together. So now that we have seen these parts, I think we are ready for the last part, which is the server board. I would say that our reference design could be used for different scope. One is the internal testing and the characterization of our silicon, our chip. And then we can use it in order to develop our software and integrate it, of course, for demos in conference or for client, for customer. Not only that, I would say that our board is also could be also used in order to reduce the design cost of our direct customer. Based on our board, the customer could easily reduce the time to the time to develop their own board. And of course, our board could be used as a platform for our partners in order to develop the software and integrate any other thing and the performance evaluation. So our board is what we call the reference design or goal design. It could be used for validation and testing of our CPU and not only our CPU, and also will be available for multiple demos. But in other words, is a multifunctional, flexible, and versatile platform. But now let's see schematics of our Seine platform. So we have here our schematics, where in the middle we have the AVB board, with RIA 1 here in the middle, and on the right, on the left side of the AVB board, we have a 2 GPU. And we have also the power board behind, the rear I/O board, a PCI Express riser card. And we can see here the schematics with the numbers of each elements that we can see here. So this kind of this kind of board, it could be used as a modular solution, and it comes with 3 different flavors for the moment. The first configuration would be a single CPU in the middle, right here, with 2 GPU on the side. And this kind of configuration, well, it could be used for AI inference, offloading memory operation workload, and training also. We have a second configuration available where we have 2 CPU, and we do not have anymore the GPU on the side. And typically, it's mostly AI inference and virtualization. And we have also a third configuration here with a single CPU, 1 GPU on the side here, and 1 SATA here, which again could be typically used for AI inference or object storage. And here we have also 2 photos of our Seine platform in construction. We see this is the second configuration with 2 AVB board here. It's fully mounted, but we still miss a few details. And well, I will conclude my presentation here with the video. So we have the AVB board with the 2 GPU, and here in the middle, we will mount our processor RIA 1. And then we can see the different configuration that we could use with this Seine platform with 2 CPU or 1 CPU, 1 GPU, and 1 SATA disk driver. Yes, I conclude with this my presentation. So thank you all.